All right, taking a look at practice exam from spring 2022. A couple things here, give the name or the molecule below. So a couple of the aromatic things we need to know. This was styrene, benzophenone, benzoic acid. Make sure we know how to do those. Draw one example each: substitution, elimination, addition, rearrangement. Normally wouldn't ask a question like this, but this was a practice, so wanted you at least be able to identify what a substitution is, what elimination is, what addition, what rearrangement is. So here, substitution is one group is replacing another. Elimination is forming a pi bond. Addition is adding something, so we're adding H and bromine. And rearrangement is actually changing its position in space. So this H ends up on this carbon there. So this carbon had 2 H's, now it has 3. So this is a rearrangement, rearranging the bonds. All right, keep going here. Now we're starting to look at the electrophilic aromatic substitution. So draw the mechanism for formation of all products, including the activation electrophile, for the reaction below. 1 sigma complex is sufficient. So the first step you need to do is make the electrophile. So the activation electrophile. You have this called an acid chloride. So the chlorine reacts with the aluminum, which is very electron deficient, forms a kind of this strange looking complex. Aluminum got electrons, so it has a negative charge. Chlorine here gave up electrons, so it's a plus charge. So the electrons are going to come down. They're going to break this carbon-chlorine bond, and we're going to make this super electrophile. That's what I call them. All right. So you can see the super electrophile here, the plus charge here. Carbon has 4 bonds. This is the more stable version, but maybe if you drew a resonance structure, it's easier to see that this carbon is going to be electron deficient, even though this is a carbocation, but it helps us understand this carbon, or this carbon is the one that's going to be reacted with the nucleophile of the pi bond. Now they have the super electrophile. We come back and do the reaction. So in the reaction of electrophilic aromatic substitution, the first step's an addition. So the pi bond from the ring reacts to the carbon that's the most delta plus, even though there's a plus charge here. This is the carbon that's electrophilic. That breaks a bond. So it formed the new bond there. We have a plus charge on the carbon adjacent to where the new thing added. So this is a sigma complex. That's just the intermediate after the addition. The aluminum with the negative charge is still there. We made that. This is also AlCl3 as a catalyst. So we also make HCl. So this, even though the aluminum has a negative charge, the chlorines all have the electron density. So the electrons in this bond between chlorine and aluminum grab the H, break that bond and make a new pi bond. So the first step in electrophilic aromatic substitution is an addition. That's the slow step because we're breaking aromaticity. The fast step is the second step, which is an elimination, right? We make a pi bond. That's going to be fast because we're remaking the aromatic ring. We also make HCl, and we regenerate AlCl3, the catalyst. All right, so for this one, which resonance structure is not possible? So you'd want to start doing resonance forms here. So what you need to remember, though, is this SO3H is an electron withdrawing group, so electrons are going to come out of the ring. So it should be a plus charge in the ring, and then if you start to practice and draw these, you'll see that this one is not possible. Won't be a possibility here. So this is the one that's not possible. Good to practice that, though. All right, give the most likely product for the reaction below. So similar electrophilic aromatic substitution. So seeing this, we know this is an electron donating group. It has a lone pair there. So it's going to donate electrons into the ring. Donating groups direct ortho or para. We have to choose. And notice here, this is pretty big, and this is a really big group as well. So I would just predict that para would be the most likely product. Now, draw the back. To do these reactions, you first got to draw how do we make the super electrophile. So the first step is the bromine, this FeBr3 to react. The bromine lone pair is going to react with the iron. It's going to form this complex where the iron has a negative charge now, formal charge, and the bromine has a plus charge. Then this bond is going to break, and we're going to form a carbocation, which is, of course, a really good electrophile, really super electrophile, as I like to call them. Now, to show the reaction, we need to show the super electrophile reacting with the ring. So we said it was going to be para. So we want to react the pi bond that is down there. So that pi bond reacts, does that addition. The group adds there, there's a plus charge here. And now in this one, you were asked to do all the sigma complexes. And remember, all that sigma complexes are resonance forms of the intermediate after the addition step. So we start drawing resonance forms. Pi bond moves, plus charge there. Pi bond moves, plus charge here. The electrons from the electron donating group can come down and also make a fourth sigma complex. There's always at least three, but if you can do the fourth, that's usually really good. And this fourth one's the best one because everyone has a full octet. So even though the plus charge is on the oxygen, the octet rule is more important. And again, just a reminder, sigma complexes are just the resonance of the intermediates. Very good. So now, to finish the reaction, let's just take that first sigma complex A, redraw it. Similar as before, FeBr4 minus. Minus is on the iron, but really the bromine's electron rich. The electrons between the bromine and iron go there. Take that H, we do an elimination to reform aromaticity, so it's a fast reaction. And you get your products, the pair substituted group, HBr, and then regenerating the catalyst. Now, like I said before, this is the most stable sigma complex because everyone has a full octet. Alright, so here we have an electron withdrawing group. The carbon attached to the ring is double bond to oxygen, makes electron withdrawing. Fluorine, even though it has lone pairs, it's very electronegative, the halogens, fluorine, chlorine, bromine, and iodine, so it's electron withdrawing. This nitrogen here is going to be electron donating, the lone pair. This sulfur is bonded to 3 different oxygens, so it's electron withdrawing. There's no lone pairs there. And then this nitrogen has lone pairs, even though it can do resonance this way, but it also can do resonance this way, so it's electron donating. Now to rank these, we'll find the most extreme examples. This is the most electron donating because it can only do resonance into the ring. The least reactive, the most electron withdrawing, is actually this because the sulfur is like this, which you should know. That sulfur is very electron withdrawing, bonded to 3 different oxygens, so that's the least reactive. The next most reactive is the electron donating group. This one's not as reactive as this because this can do resonance this way, but it's still better than electron withdrawing. Then between these two is tough. Not really sure either way it could go, so either way it's fine. I didn't really cover this. The fluorine can donate some electrons, but then it's withdrawing, so it's kind of tough to tell. So it's the kind of question maybe I wouldn't ask this year. And thanks to my son for drawing the 4. Alright, drawing some resonance structures. So overall electron withdrawing group, right? Lone pairs are not attached to the ring, so carbon double bond to nitrogen, double bond to oxygen and nitrogen, so electrons will go out of the ring, putting a plus charge in the ring, so it's a deactivator, minus charge there, moving the electrons around, make sure the arrow is going to the bond, arrow to the bond, plus charge there. Also possible is to draw the nitrogen donating a lone pair to the bond, breaking that, making the O minus there. And this is actually the most stable because this is still aromatic, so this is really good. The best resonance form, I would say this would be the best because it has no charges. Now here we're already starting with charge, so I'm just going to move this negative charge around the ring. The electrons here go to the bond. These electrons go to the atom. Negative charge there. Electrons to the bond. Pi electrons to the atom. Electrons to the bond. Pi electrons to the atom. This gives us this has no more charge now because now the oxygen's got those lone pairs, so this is actually the most stable because it doesn't have any charges. It's also, of course, still aromatic as well. Alright, so number 10 here. Indicate what hybrid orbital each lone pair is located in the molecule below. So this lone pair is in an sp2 hybrid orbital. This phosphorus is sp2 hybridized. So it has one p orbital, and that p orbital is being used for this pi bond. So the lone pair has to be in an sp2 hybrid orbital. This one, same deal. Nitrogen here is sp2 hybridized, and this p orbital is being used for that pi bond. So this is an sp2 hybrid orbital. This nitrogen is choosing to be sp2 hybridized, so it has a p orbital, so they can put that lone pair into a p orbital, which can then do resonance. Now taking it a step further, if you look at these, we're talking about aromaticity, anti-aromaticity, and non-aromatic. Aromatic things are in a ring, uninterrupted p orbital system, and have an odd number of pairs. So no sp3 hybridized atoms, so this is in a ring, 1, 2, 3, so this is aromatic. This in a ring, none of them are sp3 hybridized. 1, 2, 3 pairs, aromatic. This one is non-aromatic because this nitrogen is sp3 hybridized, has no p orbitals, no lone pairs, no pi bonds, so this is actually non-aromatic. This is in a ring, uninterrupted, no sp3 hybridized atoms, has 1, 2, an even number of pairs, so that's anti-aromatic. Same with this the cyclopropane, uninterrupted, 1, 2, anti-aromatic, even pairs. This one's non-aromatic because, again, we have an sp3 hybridized atom. This one is aromatic because carbocations are sp2 hybridized, so this has an empty p orbital, so therefore it has 1, 2, 3, 3 lone pairs. In an uninterrupted system in a ring, this would be aromatic. Alright, so below, label the molecules below as acid or base, draw mechanism arrows, and draw the products, and which side is favored. So what you'd have to do with this one, because it's not really clear, there's no charges on either of these, you have to probably draw out both possibilities, where this is the acid or this is the base to really figure this out, to see the products. Because again, I think looking at the products helps us see it. So at the end of the day, this should be the acid, this one's more acidic, this is more basic. And we can look at the products to understand why. So if this is the acid, that means we're going to deprotonate this H. And this product, even though it has a minus charge, can be resonance stabilized. Whereas if this was deprotonated, it wouldn't be able to be. So starting materials are favored. So the lone pair from the oxygen grabs the H, breaks the OH bond, and then these are the products. And this will be the situation. If you'd drawn other products, you'd see that. Again, though, which side of the equilibrium is favored is actually the starting materials, because these have no charges. All right, so finally, a kind of a challenge question. Give retrosynthesis and photosynthesis for the molecule below. So remember, retrosynthesis is a way to work backwards to try to form something. So in this, we added 2 groups. If you looked at this, we add 2 groups. You can write that out. And one group is electron donating, one's electron withdrawing. So if you want to keep reacting, you probably want to put the electron withdrawing group on last. And so that's what we do here. So one step back would be adding the ketone piece, which we can do. Then one more step back would be adding the alkyl piece. So the order we put these on matters. You want to put the electron withdrawing groups on last, right? Because they deactivate the ring. So here we put this on. So going forward, you could try this 3 carbon piece. We could do there, and again, we might put it in para, but we're just pretending this is possible here. So we put that chlorine there, and then we'd add the acylation piece, the ketone piece, with this, and the last step. And that's the photosynthesis.